Okay, some limits. Same limits we just did, but now we're going to use direct substitution and what's called the replacement theorem in the book. Okay, so a couple of things. First of all, direct substitution. It's the idea of just putting this number into the function to get the limit. Now, we know that's not always possible, but it can be made possible even when it doesn't work by using the replacement theorem. Okay? And the replacement theorem basically says this. If you can take a function where the limit can't be put in directly because it's not defined in that function, and you can simplify this to get something where the limit does make sense when we substitute in directly, that's okay. We'll get the same number. Okay? The only detail there is that if we simplify this, it can even be a different expression as long as they're equal everywhere except when x is -1. Okay? Now it's a pretty complex idea to use, but we'll just go ahead and get started with it here, and you can kind of see what I'm going to do. So, first of all, this function that I have under the limit sign, it actually factors in the numerator. The numerator is x minus 1 times x plus 1. Okay. Now, why is it helpful to factor this? It's helpful to factor because, look, I have an x minus 1 and an x minus 1 in my numerator and denominator. Now, the replacement theorem says this. You can cancel those as long as the expression that results is the same as the original one when x isn't, in this case, 1. Okay? So canceling this is okay because the only time these two expressions are different, x plus 1 and what we started with, is when x is equal to 1. Okay? When x is equal to 1, we have a problem here. We're dividing by 0. Okay? But when x is any other number, I can cancel these factors, and I'm just going to get the same thing as x plus 1. Okay? So that's the replacement theorem right there, that we can cancel these factors because it only changes the value of this function at that one point, the limit point. And remember, we're not actually, the limit point isn't really part of we don't really care what the limit is, I should say, what the function is at the limit point. So if we're only going to change this expression when x is actually equal to 1, that change is okay. Okay, now the reason we do this is that now we're finding the limit of a much simpler expression. And when x is equal to 1, this expression has no trouble, right? 1 plus 1 is 2. So we can use direct substitution now. Basically what we did is we canceled the problem algebraically, and now we can use direct substitution on this simpler expression, which is defined when x is 1. So I can just put 1 in for x, and I get 1 plus 1, which is 2. And that's the limit we found earlier. So bottom line, if direct substitution doesn't work, because doing so would give you something undefined, you can always try simplifying that expression. Canceling factors is a good example of how that can be done, to where you get something that the limit does work inside, and the limit will be the same. Okay. So we can do this one using direct substitution. Now over here, if you look at this one, this is the other example we just did with the table. We know the limit doesn't exist, and we're going to see the same thing here, but the replacement theorem does work again, and in fact, have to be a little bit careful in how I use it. Now, if you remember, the problem with this one, which we saw on the table, was when x is bigger than 0 versus less than 0, we get two different limits. So the limit from the right was not the same as the limit from the left. But what I can do is actually split this into two problems and get those limits separately using the replacement theorem. Okay. So what about if I just look at the limit as x approaches 0 from the right? Okay, these are positive values, values bigger than 0, positive numbers. Okay. Well, again, I can use the replacement theorem because the little trick here, once I look at just positive values of x, okay, this is the same thing as the limit as x approaches 0 of x over x. Okay, what did I just do there? Well, I got rid of the absolute value bars, because if we're just looking at the positive side, the absolute value of x is just x. Right? You take the absolute value of a positive number, you just get that number. Now, of course, these two things cancel, and I get the limit as x approaches 0 from the right of 1, which, of course, 1 is just 1. It doesn't matter what x is approaching, I'm going to get 1. Okay. And again, a similar trick works from the left. If I look at just that left-sided limit, okay, well, what happens? What happens now is that the absolute value of x is just x multiplied by a minus sign. Okay? That sounds strange, but when you take the absolute value of a negative number, which is the only thing we're looking at now, the absolute value is really multiplying the number by another minus sign to make it positive. Okay? So what happens here? Well, we use the replacement theorem to write this equivalent expression. That is a lot simpler, because here the x's cancel, and we get the limit as x approaches 0 from the right, I'm sorry, from the left, okay, of -1. Okay, and of course that's just -1. Okay, so, you know, breaking this into two one-sided limits, we can use direct substitution with the replacement theorem on each side.